Today we're going to continue describing data distributions using the mean and mean absolute deviation. Our objectives today are that we can use the mean and mean absolute deviation to describe a data distribution in terms of center and variability, and that we can use the mean and MAD to describe similarities and differences between two distributions. We're going to be working through part 1 of your independent practice together, so take out a sheet of paper and a pencil before we get started. Suppose that two classes of students took the same tests, and their grades, based on 100 points, are shown in the following dot plots. The mean score for each distribution is 79 points. Would you rather be in Class A or Class B if you had a score of 79? Here we have another example of two data sets that have the same mean, but the variability of the data is very different. The purpose of this is simply to get us thinking about how we interpret the data we have in front of us. There isn't a right or wrong answer about which class you would rather be in. If you scored a 79 in Class A, you would be right in the middle of the data. Some people will have scored much worse than you, but some will have scored much better. If you scored a 79 in Class B, you would still be right in the middle, but everyone would have scored close to the same as you. Look at independent practice examples number 1 through 3. Looking at the dot plots, which class has the greater mean absolute deviation? Explain without actually calculating the MAD. Mean absolute deviation measures variability. The greater the MAD, the more variability in our data set. When we look at the data, Class A clearly has more variability because its data is spread as low as 60 and as high as 91. If Liz had one of the highest scores in her class, in which class would you rather be? Explain your reasoning. To answer this, we want to look at the highest scores of each class. Let's look at the top 5 scores. In Class A, the top 5 scores are between 87 and 90. In Class B, the top 5 scores are all at 81. The top scores in Class A scored higher than the top scores in Class B, so that's where Liz would rather be. If Logan scored below average, in which class would he rather be? Use the same reasoning as you answer question 3. Pause the video until you've written down your answer and explanation. If Logan scored below average, I would reason that it is better to have been in Class B, since even the below average students are close to the mean and score around 77, whereas the below average scores for Class A are around 70 or less. Skip to exercise 7 on your independent practice. Are field crickets better predictors of air temperature than katydids? Both species of insect make chirping sounds by rubbing their front wings together. The following data are the number of chirps per minute for 10 insects of each type. All the data were taken on the same evening at the same time. Let's start by creating a dot plot to represent each type of insect. I see that the greatest value we have in either table is 68, and the smallest value is 32. Let's draw a different dot plot for each insect that includes these ranges, counting by 5 to save space and time. Once you've done this, go ahead and plot all of the values for crickets and katydids on their respective dot plots. We can see that the data we plot for crickets is all clustered on the lower end of our dot plot. When we plot the katydid data, we find that it all clusters around the higher end of our dot plot. We can conclude that the mean chirps per minute is higher for katydids than crickets, but the variability within each dataset looks similar, so we expect the mean absolute deviation to be about the same between the two. Problem 8 instructs us to calculate the mean and mean absolute deviation for each insect's data. Let's do this for crickets together, then you'll solve for katydids on your own. We first must determine the mean number of chirps per minute. To do this, we total up all 10 of the samples we took for crickets. This gives us a total of 350. We then divide this evenly between the 10 data points we sampled. This gives us a mean of 35 chirps per minute. To find mean absolute deviation, we must find the deviation of each individual cricket's chirps from the mean and total them up. Let's ignore the katydid box and instead focus on just finding the deviation from the mean for crickets. I've written in the deviations for each data value above. Remember that the absolute deviation is simply the distance away from the mean. Now we must add these up and average them out to determine the mean absolute deviation. Our absolute deviations add up to 12. Dividing this total by our 10 data points gives us a mean absolute deviation of 1 2/10. Complete this same step for the katydids. When we begin class today, we'll discuss how to solve problem 9 using your solution to problem 8.